NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new.
NASA's James Webb Space Telescope, the most advanced space observatory ever created, has given us mind-blowing views of the universe.
The most distant galaxy in the universe, the one that...
From unveiling cosmic mysteries to capturing awe-inspiring images, the JWST has redefined what we know about space. But now, something unsettling has happened.
The telescope itself has to be extremely cold.
After an ambitious mission focused on Proxima B, a potentially habitable exoplanet orbiting the closest star to our solar system, the telescope mysteriously went dark. Suddenly, contact was lost.
Just like how our eyes work, we take those three color channels, combine them together to create the full color images that we see from Webb.
Leaving scientists scrambling for answers. What did it find on Proxima B that could have triggered this?
Scientists have discovered a gigantic ring-shaped structure in space which is so big.
The unexplained silence is raising concerns, not just for the fate of the telescope, but for the monumental discovery it may have made. What was so shocking that the JWST went dark? Join us as we explore this chilling mystery and the possibilities behind what the James Webb Telescope might have uncovered. What did the James Webb Telescope discover? Proxima B, located just over 4 light-years away in the Proxima Centauri system, has long been of interest to astronomers. The exoplanet lies within its star's habitable zone, where conditions could allow for liquid water to exist on its surface. The tantalizing possibility of life existing there has driven numerous observational campaigns, but none were as promising as the recent efforts using the James Webb Space Telescope.
And that's the most exciting piece of this telescope, of this remarkable instrument we've put in space.
Equipped with unprecedented capabilities to capture the faintest signals across multiple wavelengths, the JWST aimed to probe the atmosphere of Proxima B, seeking evidence of biosignatures, geological activity, or other phenomena that could indicate the presence of life or at least a unique planetary environment. The observation campaign began with high expectations and significant public interest. The JWST had been gathering detailed data on the exoplanet's atmosphere, hoping to detect any signs of habitability or unusual atmospheric compositions. Initial readings showed some anomalies in the planet's atmospheric makeup, sparking interest among the scientific community. The telescope registered peculiar spectral lines that did not match any known chemical compounds typically found in exoplanetary atmospheres. Scientists eagerly awaited further data to better understand the origins of these anomalies, speculating on potential explanations which ranged from novel chemical processes to even the possibility of artificial structures. However, before a clear explanation could emerge, the telescope abruptly lost contact with mission control. The communication blackout occurred in the middle of a high-priority transmission window when data was being relayed back to Earth. The sudden silence left the JWST's operators bewildered, as there had been no prior indication of a malfunction. Why did the malfunction happen? The telescope systems were all functioning optimally just moments before the event. Ground-based teams immediately initiated diagnostic procedures to determine the cause of the communication loss, but no definitive explanation surfaced. The silence from the telescope left a void that was quickly filled with speculation, not only about the technical nature of the failure, but also about the data it might have collected on Proxima B. The implications of the telescope's blackout are profound. It is not merely the sudden loss of a vital piece of equipment that concerns scientists, but also the fact that it occurred in the midst of one of the most promising investigations in modern astronomy. The data being collected at the time could have potentially reshaped humanity's understanding of its place in the universe.
The universe, the good old universe, forget about quantum mechanics, okay? Just like the cosmological universe where we see all the galaxies and everything.
The anomalous spectral readings from Proxima B's atmosphere raised the possibility that the telescope had stumbled upon something extraordinary, perhaps even something that was not supposed to be discovered. One of the leading theories among the scientific community is that the telescope encountered an unexpected phenomenon near Proxima B, possibly a natural but powerful cosmic event that interfered with the telescope's communication systems.
NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new.
Cosmic phenomena such as intense solar flares, gamma-ray bursts, or magnetic storms are known to pose risks to space instruments. why Proxima B is so dangerous. Proxima B's parent star, Proxima Centauri, is a red dwarf that radiates only 0.005% of the visible light produced by the Sun and emits about 0.17% of the Sun's total energy output. Despite this low radiation, the planet Proxima B, due to its close orbit, receives approximately 70% of the infrared energy that Earth gets from the Sun. However, Proxima Centauri is a flare star, meaning its luminosity can fluctuate wildly, sometimes increasing by a factor of 100 over just a few hours. On average, Proxima Centauri's luminosity is about 0.155 times that of the Sun. Proxima Centauri's mass is around 0.122 solar masses, and its radius is about 0.154 times that of the Sun. With an effective temperature of about 3050 Kelvin, Proxima Centauri is classified as an M5.5V spectral type star. Its magnetic field is significantly stronger than the Sun's, with an intensity of around 600 Gauss, and it operates on a 7-year cycle. Proxima Centauri's close proximity to the Sun makes it the nearest known star to our solar system, sitting just 4.24 light-years away. It is part of a multi-star system, along with Alpha Centauri A and Alpha Centauri B, which form a binary star system. Over time, the dynamics of this system could have influenced Proxima B's orbit, causing it to move closer to its star. Despite its proximity, Proxima Centauri is too faint to be seen with the naked eye under normal circumstances, except for rare flares that briefly make it visible. These intense solar flares present significant challenges for planets orbiting close to the star.
You know, space is more crowded than you might think, and actually galaxies wind up interacting with each other. They actually will merge together.
Like Proxima B, as they could strip away atmospheres or disrupt the potential for habitability. The mysterious nature of Proxima Centauri doesn't end with its flares. In recent years, the discovery of planets like Proxima B has sparked immense interest, particularly given its location in the star's habitable zone, a region where liquid water could theoretically exist. However, the star's volatile nature raises concerns about the stability of Proxima B's environment and whether it could support life. The frequent solar flares emitted by Proxima Centauri would expose the planet to extreme conditions, potentially damaging any atmosphere it might have. Adding to the intrigue surrounding Proxima Centauri and its planetary system, there was an unexpected blackout involving the James Webb Space Telescope, JWST, while it was observing Proxima B. The sudden shutdown sparked numerous theories, with some experts speculating that the telescope may have been hit by a flare from Proxima Centauri, disrupting its communications. Given the star's reputation for emitting powerful bursts of energy, such an event could have interfered with the JWST's systems. However, other theories point to the possibility that the disruption was caused by something far more unusual. Some speculate that an anomaly in the telescope's software could have been triggered by the specific data it was processing at the time. It's possible that the spectral data from Proxima B contained unexpected patterns that overwhelmed the telescope's internal algorithms, causing a cascading failure. While this theory remains speculative, it opens up the possibility that the data itself, rather than an external cosmic event, played a role in the malfunction. This, in turn, raises questions about the nature of the detected signals and what might have caused them. Of course, more speculative ideas have surfaced as well. Some researchers have suggested that the JWST's blackout might have been the result of an intentional signal or structure on Proxima B that interfered with the telescope's communication systems. While these claims verge on the extraordinary, they cannot be completely dismissed, particularly given our limited understanding of extraterrestrial environments and the potential for unknown forces or technologies that may exist beyond Earth. Proxima B's position as one of the closest exoplanets to Earth has long made it a prime candidate in the search for extraterrestrial life. Its location in the habitable zone of Proxima Centauri adds to the mystery, as it is one of the few places where conditions might be favorable for life to emerge. If any signs of advanced technology or artificial structures exist beyond our solar system, Proxima B would be a logical place to find them. Any unusual signals or phenomena discovered there would not only be groundbreaking, but could fundamentally alter humanity's understanding of life in the universe. The possibility of finding evidence of life or even extraterrestrial technology on Proxima B has fascinated scientists and the public alike for decades. With advanced instruments like the JWST, we now have the capability to investigate these possibilities in greater detail than ever before. However, the notion that the telescope may have encountered something so unusual that it disrupted its own operations only deepens the mystery. What could the JWST have detected around Proxima B? Was it a natural phenomenon, an unknown cosmic event, or perhaps something far more extraordinary? These questions linger as scientists work to unravel the secrets of the data, leaving us to wonder what discoveries may lie ahead in the unexplored depths of space. Theories on what the mysterious finding was. What if the JWST had indeed captured definitive evidence of something beyond our understanding? What if the data it was collecting on Proxima B hinted at a form of life or a structure that defied current scientific paradigms? Such an event would not only be a groundbreaking discovery, but also a potentially paradigm-shifting one that could challenge our assumptions about life, intelligence, and technology in the cosmos. The scientific implications of discovering unusual data on Proxima B could extend beyond biology and planetary science. It might provide new insights into astrophysics, chemistry, and the conditions necessary for life. If the anomalies detected in the planet's atmosphere were indeed caused by biological processes, it could reveal previously unknown mechanisms of life that exist under different conditions from those found on Earth. Alternatively, if the anomalies resulted from non-biological processes, they could point to new geological or chemical phenomena that have yet to be understood.
James Webb Space Telescope has hardly opened its eyes, and the universe is new.
The findings might also force a reassessment of how habitable zones are defined, potentially broadening the search for life to include more extreme environments around other stars. Should it turn out that the telescope detected some form of artificial structure or signal, the implications would be even more staggering. Humanity's place in the cosmos would have to be rethought, as the discovery of extraterrestrial technology would indicate that we are not the first species to develop sophisticated tools, and that intelligence may not be a unique trait of Earth's biosphere. Such a revelation would force a reassessment of what we consider civilization, and might even lead to a re-evaluation of the technologies and sciences currently believed to be the pinnacle of human achievement. However, the prospect of such discoveries remains hypothetical. The actual cause behind the JWST's blackout is still unknown, and it is possible that it was merely a coincidental technical failure unrelated to the data being collected at the time. Yet the timing of the incident invites deeper contemplation. It challenges scientists to confront the limits of current technology and raises questions about what could happen if humanity were ever to encounter evidence of extraterrestrial life or advanced technology in a direct and unambiguous manner. Would our current scientific paradigms be equipped to handle such a discovery? Or would it require a complete overhaul of our understanding of reality? In the immediate aftermath of the JWST's sudden silence, there has been a renewed interest in establishing a more resilient system of communication and redundancy in future space missions.
The telescope will be so powerful. People will be simply blown away because they will not be able to recognize.
The incident has exposed vulnerabilities in current space exploration methodologies, highlighting the need for systems that can continue to function even if a primary communication channel is lost. It has also sparked a call for more collaboration between space agencies, as a collective effort may be required to investigate and interpret such mysterious phenomena in the future. As the investigation into the cause of blackout continues, the incident has also reignited public interest in space exploration. It serves as a reminder that despite all the advancements in technology, the cosmos remains a place full of mysteries and potential surprises. The unknown can be both a source of fear and a wellspring of curiosity. The idea that the universe might harbor life or advanced technology beyond Earth remains a driving force behind humanity's desire to explore. The JWST's mysterious blackout, rather than dissuading further investigation, has only deepened the desire to uncover the secrets of Proxima B and similar exoplanets. But this incident is not just an isolated technical setback. This has happened before. It is a reminder of the challenges faced when exploring the frontier of the unknown. Proxima B, while close in cosmic terms, is still far beyond the reach of any crewed mission in the foreseeable future. The nature of the information we gather from distant targets, such as exoplanets, is inherently limited by the tools we use and the methodologies we apply. Spectral analysis, one of the primary techniques for studying exoplanetary atmospheres, provides us with indirect evidence about the chemical composition and potential processes occurring on distant worlds. However, this method only gives us part of the picture. Spectral anomalies or unusual data patterns can suggest intriguing possibilities, but they rarely provide concrete, definitive answers. The peculiar signals detected on Proxima B just before the JWST blackout perfectly illustrate this limitation. These signals hint at something out of the ordinary, but without additional data, the exact nature of this something remains a frustrating and tantalizing mystery. The questions raised by this incident extend far beyond technical malfunctions or basic astrophysical curiosity. They touch on deeper issues about the boundaries of current technology, our interpretation of ambiguous data, and the potential for discoveries that challenge our understanding of the universe. They touch upon philosophical considerations about humanity's readiness to confront evidence of extraterrestrial life should it be found. If the James Webb Space Telescope did indeed capture data hinting at life or even technological artifacts on Proxima B, it would not be the first time that scientific evidence has forced society to grapple with uncomfortable new realities. The history of science is filled with instances where new discoveries have upended established views, leading to intense debates and paradigm shifts. For example, the heliocentric model of the solar system, germ theory, and quantum mechanics all fundamentally changed our understanding of the universe and our place within it. The discovery of extraterrestrial life, or even evidence suggesting the possibility, would likely be one of the most profound shifts in human history. The mere possibility that an advanced form of life could exist on Proxima B raises intriguing questions about how such life would manifest. Would it resemble Earth-based biology, following the same chemical and molecular principles, or would it represent something entirely alien to our understanding? The anomalies detected in Proxima B's atmosphere could theoretically correspond to life forms that do not conform to our expectations of carbon-based, water-dependent biology. They might utilize alternative biochemistries that we have not yet considered, or they could represent life forms that inhabit atmospheric layers rather than planetary surfaces. If life on Proxima B follows different biological principles, it could be a sign that life itself is a far more versatile and adaptable phenomenon than currently believed. On the other hand, if the data indicates the presence of technological signatures, the implications would be even more far-reaching. A technological civilization on Proxima B would not only suggest that life is abundant in the universe, but also that intelligence and the development of complex societies are not unique to Earth. It would challenge the Great Filter hypothesis, the idea that certain steps in the evolution of life are exceptionally rare, serving as barriers to the emergence of intelligent species. If the data hinted at artifacts or signals of non-natural origin, then it would suggest that the Great Filter might not lie in our past, as some have speculated, but could instead lie ahead of us, presenting existential risks that all advanced civilizations must navigate. If there were indications of technology on Proxima B, then a new question would arise. How would a civilization located on a planet orbiting a red dwarf star with vastly different environmental conditions compared to Earth develop? Proxima Centauri emits only a fraction of the light that our Sun provides, and the planet itself is subjected to intense stellar flares. These conditions would likely shape any potential technological advancements in ways that differ dramatically from those of human civilization. For instance, a civilization on Proxima B might need to develop extraordinary measures for shielding against radiation, possibly leading to entirely unique materials or energy-harnessing techniques. Their cultural and technological priorities might revolve around surviving extreme space weather, potentially resulting in innovations we have yet to imagine. The Blackout incident may also influence future space exploration missions, emphasizing the importance of diversifying observational strategies. As astronomical technology advances, telescopes and probes will increasingly need to operate autonomously, employing artificial intelligence to make decisions when communication with Earth is compromised. The loss of the JWST during its observations of Proxima B has highlighted the need for robust fail-safes and more adaptable systems that can continue to collect data even in the event of communication disruptions. This could mean developing new ways to transmit information across greater distances or implementing automated protocols that allow space instruments to prioritize and store data when contact is lost. Moreover, the sudden silence from JWST has underscored the necessity of multi-mission collaboration. Space telescopes such as Hubble and even future missions like the Nancy Grace Roman Space Telescope could be employed in tandem to cross-check findings and ensure that no single point of failure can jeopardize an entire line of inquiry. Interagency cooperation among NASA, ESA, and other international space organizations would also enhance data sharing capabilities, ensuring that important discoveries are verified through multiple independent observations. Such a coordinated approach would improve the resilience of space science, making the search for life beyond Earth less susceptible to the loss of a single instrument. The incident could have broader implications for how space missions are prioritized and funded. With the apparent vulnerability of high-stakes observatories like the JWST, there may be a shift toward investing in a more diversified portfolio of smaller, more numerous instruments that could complement large flagship projects, providing a safety net in case a critical instrument like the JWST goes offline. In this way, the pursuit of answers would not be entirely dependent on any single telescope. This diversified strategy could also foster innovation by encouraging the development of more specialized, smaller-scale technologies designed to target specific types of data or phenomena. Other mysteries of Proxima B researchers have also made significant progress in solving the puzzle surrounding a distant galaxy encircled by a nearly perfect Einstein ring, discovered by the James Webb Space Telescope. The galaxy in question appears denser than it should be, and scientists now suggest that this unusual density is due to a massive halo of dark matter compressing the galaxy. Einstein rings, first predicted by Albert Einstein's theory of relativity, are luminous rings formed by a phenomenon known as gravitational lensing. This occurs when light from a distant object is bent by the gravitational pull of a foreground object between the distant object and the observer. The light seems to bend, though it actually travels in a straight line through warped space-time caused by the mass of the foreground object. In September 2023, astronomers discovered such an Einstein ring named JWST-ER1 in the JWST's data. This structure has two components: JWST-ER1R, the glowing ring formed by the distant galaxy's light, and JWST-ER1G, the foreground object that warps this light. JWST-ER1ER is located around 21 billion light-years from Earth, making it the most distant gravitationally lensed object ever detected. Scientists estimate that this galaxy formed approximately 10.3 billion years ago, just 3.4 billion years after the Big Bang. When researchers first observed the lensing object, JWST-R1G, they noted its unusual density. The mass surrounding the galaxy was estimated at around 650 billion times that of the Sun, a remarkably high value for a galaxy of its size. Although dark matter, a mysterious substance making up about 85% of the universe's mass, explains much of the weight, the galaxy still appeared too massive for its size. Additional mass is needed to explain the lensing results, the researchers initially stated, though they couldn't specify what this extra mass might be. A new study, published in the Astrophysical Journal Letters on April 11, 2024, offers an intriguing explanation. The dark matter surrounding JWST-ER1G is being compressed into a tighter space by collapsing regular matter. This compression results in the higher-than-expected density. Lead author Damao Kong of the University of California, Riverside explained that their numerical studies confirm that this mechanism could account for the elevated dark matter density observed. This isn't the first time JWST has uncovered an Einstein ring. In September 2022, a Reddit user sifted through the telescope's data and found a perfectly circular ring of light about 12 billion light-years from Earth. JWST has also used gravitational lensing to capture the universe's most distant star and some of its oldest galaxies. These discoveries highlight the telescope's role in exploring the early universe and understanding the role of dark matter in shaping galaxies. Scientists are optimistic that JWST will reveal even more Einstein rings, helping to test these theories and uncover new insights about dark matter. The continuous discovery of Einstein rings offers valuable opportunities to study dark matter, a substance that remains one of the most elusive components of the universe. Each new observation adds to the growing body of evidence, allowing researchers to refine their models and theories regarding dark matter's influence on galactic formation and evolution. As JWST continues to probe deeper into space, scientists hope to unravel more mysteries about the interactions between dark matter and regular matter, potentially shedding light on the origins of the universe itself. Is there alien life on Proxima B? If the anomalies observed on Proxima B were indeed caused by artificial means, it would revolutionize our understanding of extraterrestrial phenomena and open an entirely new field dedicated to recognizing and studying non-terrestrial technological artifacts. Even in the absence of concrete evidence of life or advanced technology, the investigation into anomalies like the JWST's Blackout could lead to profound scientific and philosophical revelations. One such insight is the critical need for caution when interpreting data from exoplanets.
Each planet attracts all of the other planets,
particularly those in the habitable zones of their stars. The search for extraterrestrial life is inevitably shaped by our Earth-centric perspective, which is restricted to a single biosphere. Researchers are therefore tasked with expanding the frameworks they use to detect life beyond the familiar benchmarks of carbon-based chemistry, atmospheric oxygen, and the presence of liquid water. Anomalies that deviate from these established patterns could be the key to uncovering alternative forms of life, provided scientists remain open to exploring unconventional explanations. In doing so, they may discover entirely new biological or technological paradigms that challenge everything we currently understand about life in the universe. If a spacecraft were to lose communication with Earth, advanced AI systems on board could continue to function autonomously, storing the most critical findings and transmitting them once contact is restored. This ability would significantly enhance space exploration, allowing missions to adapt on the fly to unexpected challenges while ensuring no valuable data is lost. Such resilience could be transformative, enabling future spacecraft to operate effectively, even in the face of technical setbacks or communication delays. Additionally, there's growing interest in deploying distributed space telescope arrays rather than relying solely on a single large, multi-purpose observatory like the James Webb Space Telescope. The concept involves deploying constellations of smaller, specialized telescopes across different orbits, or even placing them at various points throughout the solar system. By observing distant objects from multiple perspectives simultaneously, this approach would not only provide redundancy in case of system failures, but also significantly expand observational capacity. These distributed arrays could offer simultaneous coverage of different wavelengths or multiple targets, providing more comprehensive and versatile data to support scientific discovery. If one instrument in a distributed space telescope array were to go offline, the other components could continue their operations, significantly reducing the risk of catastrophic data loss. This redundancy enhances our ability to detect subtle signals that may point to signs of life or reveal unique planetary processes. The recent interest generated by the JWST Blackout, particularly its potential link to Proxima B, might expedite the timeline for ambitious space missions aimed specifically at detecting extraterrestrial life. In fact, this renewed focus could lend greater momentum to initiatives like the Breakthrough Starshot project, which seeks to send tiny, light-propelled probes to the Alpha Centauri system. The mystery surrounding Proxima B may prompt increased funding and public support for these missions, accelerating their development. By leveraging cutting-edge technologies and maintaining a dynamic, adaptive approach to space exploration, humanity could be one step closer to uncovering the secrets of life beyond Earth. By sending small, fast spacecraft equipped with cameras and instruments capable of gathering direct data from nearby star systems, humanity could achieve an unprecedented level of detail in the study of exoplanets like Proxima B. The Blackout incident could thus act as a catalyst for the development of these new mission concepts, pushing the boundaries of exploration technology even further. The event may prompt a reevaluation of the kinds of exoplanetary signatures that scientists prioritize in their search for life. Historically, the search has focused on finding Earth-like conditions, liquid water, a stable atmosphere, and an energy source. However, the strange atmospheric signals detected from Proxima B suggest that life could exist in forms or under conditions we have not yet considered. This could lead to a broadening of the criteria used to assess habitability. Scientists might start to investigate more exotic biosignatures, including atmospheric or geophysical characteristics that do not directly mimic those found on Earth. For instance, gases or specific isotopic ratios that might initially seem unrelated to biological activity could be revisited for their potential to serve as indirect indicators of life, particularly in atmospheres that are dramatically different from Earth's. What might appear insignificant in one context could, in an alien environment, be a crucial signal of biological or planetary processes. Another intriguing direction that the JWST Blackout may spark interest in is the search for techno-signatures, evidence of technology or industrial activity on other planets. Traditionally, the search for extraterrestrial intelligence, SETI, has focused heavily on detecting radio signals, but this may be too limited in scope. The concept of techno-signatures opens up new possibilities for finding signs of extraterrestrial civilizations through other means, such as detecting pollution or artificial light sources. Future space observatories may also need to evolve in terms of their structural resilience, particularly in protecting against cosmic radiation and stellar flares, especially when observing systems around volatile stars. One promising development could be the implementation of adaptive shielding, a system that dynamically adjusts in response to environmental changes in space. This technology would enable telescopes to automatically react to sudden spikes in radiation or unexpected cosmic events, providing better protection and minimizing the risk of disruptions like the JWST incident. With these advancements, next-generation telescopes could become even more reliable, enabling longer and more fruitful missions in the pursuit of detecting life and understanding the universe. The event has stirred the imaginations of people around the world, fueling both excitement and anxiety about the possibility of first contact. This psychological impact could shape public policy, influencing funding for space exploration and guiding international efforts toward collaborative approaches in handling discoveries that could reshape humanity's view of itself. The mysterious nature of the JWST's Blackout, paired with the anomalous data from Proxima B, has led to renewed interest in contingency planning for potentially disruptive space-based discoveries. Alright, so that's it for this video. And if you want to watch more amazing content like this, check out some of our other videos. Bye!